Okay, welcome back. For our next talk, I would like to welcome Dr. Waldemar Martens from the European Space Agency. Waldemar wants to measure gravitational waves, and he is the mission analysis lead of LISA, which is an experimental setup consisting of 3 satellites flying around in space millions of kilometers apart, shooting lasers at each other, all to measure extremely small changes in distance. Besides this really cool space physics stuff, Waldemar is also the project manager of the Mission Analysis Tools software project. And although this is not the topic of this talk, it made me think that maybe he has more in common with us earthly TNG software developers than we think. Waldemar, we're looking forward to your talk. Thanks for being here today.
Good afternoon, everybody. Thank you very much. I'm glad to see the room full. Looks like people are interested in this. And I'm not going to measure gravitational waves all by myself. It's a huge team behind that. And I hope you get a glimpse of all that is involved in this project today. So I will cover mostly 4 topics. First, I'll introduce what are gravitational waves, what are we want to measure. Then I will talk about the LISA mission, how it is set up, and the science behind the mission, what are we going to measure. And then I'll talk about the LISA instrument and the data analysis, which might be the most interesting aspect for the people here in the audience. And I hope I'll have enough time for that. What are gravitational waves? Imagine you have a perfectly still ocean, and you have these 2 boats. They don't move relative to each other, they are still. And then you have a wave coming from one side, and what happens is, well, the boats start to move, but most notably, the relative distance between the 2 boats changes. So if there were 2 people on these boats and they were attached with a rope or any measurement device, they would be able to tell that there was a wave passing by without even looking at the water. And that's more or less also what gravitational waves are, except that the waves don't travel through water, but through space-time. Space-time is an elastic medium. It can bend, and it does bend, and that's what we're going to measure, or what we want to measure with LISA, and that what has already been measured in LIGO and Virgo from ground. So the important concept here is test masses. So the boats were our test masses on the ocean, and with gravitational waves, we will speak a lot about test masses as well. If you put a bunch of them in space and you have a gravitational wave passing towards you, then the masses would look like this. So they will wobble in this pattern, and if you want to see it from the side, you can actually tell that it's a wave because it's traveling from the left to the right. And also from this perspective. So it's really, the effect of the gravitational wave is how it changes relative positions of little test masses. Like with light, we have 2 polarizations. With light, we have the vertical and horizontal polarization. In gravitational waves, we have the plus and X polarization. This is just 40 degrees tilted. And then you can, of course, have any linear combination of those, and then it can look even more complicated, the motion. This is a monochromatic gravitational wave. It means it has a single frequency and a definite propagation direction. The reality, of course, is a lot more complicated. If you look into space, there's millions of sources of gravitational waves, big, small, different frequencies, different directions, and it's a very complicated motion of test particles that you would encounter, and that's also one of the big challenges of the data analysis, which we'll talk about later. The first detection of gravitational waves happened from ground in 2015 by the LIGO-Virgo collaboration, and it was awarded the Nobel Prize in 2017. Okay, I see it's not so well visible, but it's here, this animation here. What was measured by LIGO Virgo is two colliding black holes of the sun, of the mass of around 30 solar masses each. Play it once again. No. So basically what you see, these two black holes, they spiral, and as they spiral, they emit gravitational waves. It's similar to if you have electric charges. If they are accelerated, they emit electromagnetic waves. Here we have masses instead of charges, and we have gravitational waves instead of electromagnetic waves. But the idea is the same. And the moment they collide is when the maximum amplitude of gravitational wave is emitted, and that's actually also what is measured on ground. You see these detectors are built like two large laser beams perpendicular to each other, each 3 to 4 kilometers long, and then they send the laser in both directions, and they will interfere at the crossing. I'll show in more detail later. And the waves that were measured by LIGO and Virgo can actually be made audible because the frequencies happen to be in the audible range. So like 20 hertz to 10 kilohertz. And that's what they actually do. They convert it into a signal and they play it through loudspeakers. And that's what we're going to do as well. So what you will hear now is the signal that was measured by LIGO Virgo. First, at the original frequency, it will be a bit hard to hear, maybe. It will be twice on the original frequency and then twice at a higher frequency to make it more audible, let's say. So what is noticeable is the chirp in the end. That's the moment where the bodies collided and the moment where the largest amplitude was emitted, and that's what is clearly audible and also visible in the spectrum. I should have mentioned these deviations that we are measuring are tiny. They are nothing compared to the boats that I showed you earlier. For LIGO, they are at the level of 10 to the minus 18 meters, less than an atomic nucleus. For LISA, it will be larger, 10 to the 12 meters, but still, it's tiny. How can you measure such a small deviation, in test masses? The only chance you might have is with interferometry. And okay, I don't have to explain to this audience what interferometry is. Basically, you have two sine waves which you can interfere constructively or non-constructively. And then you might see a signal or you might not see a signal. And that's what's done in this Michelson-type interferometer. That's why we have this arrangement of two perpendicular arrays. Oh. I'm trying to find the mouse. Here, okay. No. So the way this works is you have a laser, you have a beam splitter, two mirrors at the ends, and then a detector here. So the laser travels through both directions and gets reflected at the mirror and then goes back to the beam splitter and to the screen. Depending on what the relative distance of these two arms is, you get a constructive or destructive interference on the screen. So it means if you move one of the mirrors a very tiny bit, you can already detect it on the screen by a small change in the brightness of the signal. So with this technique, you are able to measure deviations much less than the wavelength of the laser you're using. And that's the principle that was used in LIGO and Virgo, and that's also the principle that will be used in LISA. Why do we want to go to space if we can already measure gravitational waves on ground? There are several reasons. First of all, it's a very quiet environment. Here on Earth, you have trains, you have earthquakes, you have atmospheres, so many disturbances, and you have to isolate the detector from all of them because you want to measure such tiny deviations. In space, it's already a lot quieter because you don't have all these effects. In space, you have the vacuum, so the laser beam can travel a long path completely undisturbed, and you can build detectors of a much greater arm length, which means you can achieve a higher sensitivity and you can go to lower frequencies. And to compare LIGO and Virgo with LISA, here is a basic, like the main features. LIGO Virgo, you have an arm length of 3 to 4 kilometers. With LISA, we will have 2.5 million kilometers. So the distance between the Earth and the Moon is 380,000 kilometers. It's much more than that. And that translates directly into the frequency that we're sensitive to. Whereas in LIGO Virgo, we were sensitive to the audible range. With LISA, we will go to the sub-hertz frequency range. And what does that mean in terms of sources that we will be able to measure? It means we can measure much more violent, let's say, events like colliding black holes of 10 to the 3 to 10 to the 7 solar masses. So these are typically black holes that you have in the center of galaxies. So when two galaxies collide, the two center black holes collide as well. And these are the signals that we will be able to measure with LISA. And okay, you cannot do this with ground-based detectors. It doesn't mean that one or the other is better. They're both complementary. It's a bit like in optical astronomy, you have the visible light, the infrared, the X-rays. So you need all of them to get different information from the universe. Just very briefly about the history of LISA, just to say the idea has been around for quite a while. The first ideas came about in the 70s. It was proposed first already in the 90s as a mission. Only now, in 2024, the mission got adopted by ESA, which means we committed to actually build it. So it was quite a long path. What is important and what I will talk about also on one slide is LISA Pathfinder, which was launched in 2015, which was not a science mission, but a pure technology demonstrator. What is LISA Pathfinder? So to measure the effect of gravitational waves, you have to make sure that your test masses are 100% freely falling. What does it mean to free fall? Well, you go on a bridge, you throw a stone into the water, that's kind of a free fall, no? Not entirely, because you have the air resistance, for instance, which breaks slows down the stone. Even if you go into the vacuum, into space, you have the solar radiation pressure, which influences the motion of the body, and many other effects that you could have. A free fall means that you're influenced by gravitational forces only. You have to switch off all other disturbances and make sure you're only impacted by gravitational forces. And that's what LISA Pathfinder was bound to show and did it very well. And the way it worked, it had two test masses on board. It's shown schematically here. You have two test masses and some interferometers. This test mass 1 is put at the center of the satellite in free fall. It means it's completely isolated. It's in an internal vacuum. It's in a shielded housing, so it's shielded from electromagnetic interference. And the spacecraft flies around the test mass. So basically, the spacecraft makes sure that the test mass doesn't touch the walls of the housing. And the way it is done is via interferometry. So when the interferometer detects the spacecraft has moved, the test mass has moved towards one of the walls, it will fire the thrusters and steer the spacecraft in the same direction to make sure that the test mass always stays hovering in the middle. Then you have the second test mass, and this is not freely falling, but this test mass is made sure to have always the same distance from the test mass 1. This is also made sure by interferometry. And then there is a electrostatic force acting on test mass 2, which will make sure that this distance is held constant. And from knowing this strength of the control force that you have to impart on the test mass and the geometry of the setup, you can infer how much non-gravitational noise there is in your system. How much of the acceleration that you're measuring is actually non-gravitational. And the way this is depicted, and you will see these diagrams, some more of these diagrams later, so get used to them. You have the frequency on the x-axis that will later be the frequency of the gravitational wave, but here it's basically the frequency of the noise that we are measuring. And on the y-axis, we have basically a measure of the free fall. The lower we are on the y-axis, the better the free fall, the less non-gravitational noise there is. So we want to be as low as possible. And when LISA Pathfinder was launched, we had a requirement to be here, to be below this region here. And at the end of the mission, we went even down below the LISA requirement. So the LISA Pathfinder mission was a huge success, and that's also why it fueled the LISA mission at that point. So LISA Pathfinder was a spacecraft that was placed in the Lagrange point 1 between the Sun and the Earth, just because it's a very quiet point and it was very suitable for that mission. Okay, now we come to the LISA mission. The LISA mission will be 3 spacecraft, not 1, and they will fly in a triangular formation. Each will be equipped with 2 lasers, and they will connect via laser link with an arm length of 2.5 million kilometers. And each pair of arms constitute a Michelson interferometer or Michelson type interferometer, and when a gravitational wave passes by, it will slightly disturb those arms, and this will be measurable in the interferometric measurement system. Essentially, you could take each pair of arms, and it would be like a Michelson interferometer. So to show this a bit more clearly, what happens in a vastly exaggerated way, so you have this triangle. When a gravitational wave passes by, you get this kind of distortion, wobbly motion, and that's how you know that you have a signal. LISA will be placed in an orbit around the Sun, following the Earth by 20 degrees, or before the Earth, both are possible. And each spacecraft will have 2 test masses. Basically, at the end of each laser arm, there is a test mass, and that's how you actually measure then the signal. And the orbit is particularly cool in LISA because it's doing this cartwheel motion. You have this triangle, and while it travels around the Sun, it's also cartwheeling. It's kind of moving around its own axis, and after 1 year, it also completes a rotation around the constellation center itself. And it's a very peculiar kind of orbit because it's very stable. These are basically just Keplerian orbits, with plus the disturbance of the Earth and the other planets. But even with 2.5 million kilometer arm length, you can get a triangle stable to 60 degrees plus minus 1 degree. So it's just a very suitable orbit for this kind of mission. Okay, I will skip this one. Now, what are we going to measure with LISA? I already showed you this kind of graph. So to explain again, here we have on the x-axis the frequency of the gravitational wave, and on the y-axis we have the strength of the gravitational wave. The louder the source, the higher it will be on the y-axis. So if you have a given gravitational wave source, it will be a point in this graph. And then we have the sensitivity curve in green here, which means every source that is above the curve will be measurable by LISA. So everything that is below is drowned in the noise of the instrument. So we cannot access it. So then, of course, the question is, what sources are there above the curve? And there's plenty of them. No, doesn't work. It's got hung up. Okay. So first of all, something not so interesting, there's this so-called confusion noise. So there's, in our galaxy, in our Milky Way, there's many galactic binaries, small black holes, white dwarfs, which are emitting gravitational waves. And there are so many that LISA will not be able to distinguish them. They're so close in frequency, and they are so close above the noise curve, it will be just like a foreground. It will just basically add on top of the noise. But then there will be sources in our galaxy, again, which we can resolve. So for instance, after 1 year, we expect to resolve kind of this amount of binaries. And then there are so-called verification binaries. These are binaries that were already measured by electromagnetic observatories, so we know there are these sources, where they are in the sky, and how much, where they will land in this plot. And they're just needed to verify our instruments, so we want to measure them definitely. And then after 4 years, we will see much, much more, once we get more data, more resolution. And as I said, there is white dwarf binaries, white dwarfs with neutron stars, black holes with neutron stars, black hole binaries. There's lots of different sources just in our galaxy. Then there's stellar mass black holes. These are the black holes that were measured by LIGO, for instance. And you see they are at a higher frequency. LIGO is a smaller detector. It's sensitive at a higher frequency. But LISA will be able to see some of them when they are far apart, right? So LIGO saw them when they were colliding, when they were very fast, the frequency was high, but very few months or years before that, they are at a lower frequency, and LISA will be able to say, okay, LIGO, in 2 months, have a look, you will see a signal there, basically. And these are the real interesting new sources. These are the massive black holes, which I talked about earlier, which are in the center of our galaxy, for instance. And they are really loud. They have massive signal-to-noise ratio, and they do such a curve, basically, in this plot. So they start here at a lower frequency when they're far apart, and as they spiral in, they increase in the frequency, and then at the point where they collide, they do this chirp, and then the signal is gone. And we expect to see, I think maybe in the order of tens of such signals in LISA. Then there's an interesting source called extreme mass ratio inspirals. These are binaries where you have a massive black hole and then maybe a small black hole which circles around it. And these cause very weird, complicated signals, because they're extremely relativistic. So if you look at the orbits of these stellar system, they're nothing at all Keplerian. They're like, they go kind of really like in all directions, and there doesn't seem to be any pattern. And these are shown here in this frequency graph. LISA will also be able to do cosmology. You probably know that the universe is expanding, and the way we know this is by measuring the redshift and the distance and then seeing that the further away, the higher the redshift the stars or the galaxies are. So the larger the distance, the larger the redshift. So the farther away, the faster they're moving away from us. And with LISA, we will be able to do an independent measurement of the luminosity distance. And if we can observe the same source with an electromagnetic counterpart, like for instance, this is Athena, this is another ESA mission which we'll observe in the X-rays, then we can get an independent measurement of the Hubble constant. And if you ask me, what is the coolest thing that LISA will hopefully be able to measure, it's this. And I think many people agree, because it will really tell us something, if we will be able to measure it, about the Big Bang or about the origin of our universe. The earliest direct signal we currently have from the Big Bang is the cosmic microwave background. That's where the electrons and the nuclei recombined to form atoms, and the universe became transparent, essentially. But that happened 380,000 years after the Big Bang. In the cosmic timescale, it's shortly after the Big Bang, but still there's a lot that happened before that. And especially in the very first fractions of a second, there were violent gravitational things going on, like for instance, maybe inflation, or there are theories about cosmic strings and phase transitions, and all these things that happened predict to emit gravitational waves. And there are, of course, many models. It's very speculative, but many of these models say, okay, if this model is correct, then in the LISA band you should see such and such a signal. And this would tell us really something new about our universe, and this I find the most exciting. All right, now let's come to the instrument. When I showed you earlier the Michelson interferometer with a nice interference of of the two laser arms, I basically assumed it's a perfect laser. It means that you have a nice sine wave on both arms and they nicely interfere and you get a clean signal. Reality is not like that. In reality, when you have a laser, you have what's called laser noise. And I tried to visualize it here. Basically, you're not getting a perfect sine wave, but you have small deviations. And of course, if you have such a laser signal and you're trying to interfere two of such signals, you're never going to get a clean destructive or constructive interference. And even worse, the level of this laser noise, although it's small, 10 to the minus 13, it's still 7 orders of magnitude higher than the signal of the gravitational waves that we want to measure. So it sounds like a disaster in the first look. But on ground, there's a fairly simple solution to this. And this is simply solved by choosing exactly equal arms. And I will show you how this works. So now we're going to look at the phase of each of the laser arms and see how the effect of such a noise will have on the phase. So basically here in this arm, you will see the phase that arrives here and the one that is by 2 arms, twice L1 delayed. And the little wiggle here, it's not a gravitational wave signal, it's a laser noise. So this is completely without gravitational waves, just the instrument by itself. On the other arm, we have the same. You measure the signal itself and then the delayed signal. When you interfere both on the detector and you assume that the arms are equal, they exactly cancel out. So it means if you design your detector with equal arms, the laser noise just disappears. And it's great. However, in space, we cannot build a detector with equal arms because of orbital mechanics. The triangle, just by the natural motion, will wobble around. I said earlier, plus minus 1 degree, the corner angle, but that also means that the arms wiggle around. And roughly 20 years ago, somebody came up with a really cool solution to that, and the solution is to record the data of each arm individually. So maybe I should swap back and forth. So this is the classical interferometry setup where you just have one detector, but now we're going to detect each arm individually, and then we're going to do the interference in post-processing on ground digitally on the computer. Why does this work? So basically you see, if you record this signal here and delay it by the second arm length, so the other one, and you record this signal here and record it by the first, and delay it by the first arm length, you get this collection of terms, and you see it all cancels out. What you need to know, of course, is precisely how long is your arm, because you need this as an input to do this delay. It's called time delay interferometry. But in LISA, we can determine the arms to the absolute length of the arms to the precision of a meter or so. So to give you an analogy, basically what we're doing, instead of recording a full choir, we're recording the individual voices, and then when somebody or one of the singers is out of time in post-processing, we delay them to make it all coherent again and make it sound like a professional choir. Okay, what data do we have in LISA? How does the signal look like? I talked earlier about the different sources, and all these sources, they appear simultaneously in the data stream in one of these signals that we construct as I showed on the previous slide, in the time delay interferometry variables. So we have the verification binaries, these are the galactic binaries in our galaxy. We have these extreme mass ratio inspirals. We have these very loud, massive black hole binaries. Then we have the galactic binaries, which are not verification binaries, and then we have the noise. And that's all in one data stream. So it's a very dense signal. If you look at it in the frequency domain, it still looks quite dense. Although some things are separated in frequency, it's a very complicated data analysis problem to disentangle all the different sources. Again, to draw an analogy, imagine you have this huge symphonic orchestra, and you're given the task, listen to this, and then transcribe the violins, the tubas, the trumpets, the timpani, the choir, all the individual voices, transcribe them on a sheet of paper. And that's, of course, not an easy task, but there are techniques to do that. First of all, what you would do is, of course, learn how does a violin sound exactly, how does a trumpet sound exactly. And that is what is done with the waveforms. Basically, we want to calculate the waveforms, what signal do we expect in the detector from massive black hole binary, from extreme mass ratio inspiral, etc. And once we know them, we can at least theoretically construct what we will see in the detector when we sum it all up. And some of these, so to calculate these waveforms, you need, of course, general relativity. Some of these motions are extremely relativistic, and depending on where you are in this diagram, where you see the mass ratio of the two binaries, of the two bodies here, and the compactness here, if you have two very similar bodies and they are very close together, you're of course extremely relativistic. You have to do numerical relativity. You have to fully simulate the full system, and that is very expensive. You have runtimes in the order of days or weeks. If you have large bodies, but they are far away, this is actually the simplest. You can do post-Newtonian theory, you have analytical formulas, and you have very fast runtimes. And then there's, on this other extreme, we have this what's called gravitational self-force, where you have one large and one small body, but they are still close together, and then you have to take into account the effect of the small body on the space-time in which it is moving, so kind of the self-force effect. And that is also still expensive. And then what you do is Bayesian inference. I assume many here are familiar with this, if they are from experimental physics. Basically what you're trying to do, you're trying to fit a parameters of your model. So for instance, assume the simple sine with a frequency drift. The more data you collect, the more you're able to narrow down the parameters, and you do this with the Markov chain Monte Carlo. And you're not only getting the parameters, but you're also getting the probability distributions around these parameters. Of course, you have many more sources in LISA, and what is done is the so-called global fit, where we expect around 60,000 parameters after 1 year of data, of observation, and we need to fit them all at once. It's not done really all at once. There are techniques, for instance, to first compute the loud sources and then subtract them. But in the end, you want to run a fit where you allow all parameters to be free and fit to your signal. And the calculations that we currently have, using a limited set of sources, so simulated sources again, right? And 12 months of data run, for instance, 5 days on 8,000 CPUs and 7 days on 4 GPUs. But we expect more sources, of course, than what's been simulated. So it's an active field of research, how to do this global fit in LISA. And then finally, just to wrap everything up, how the data analysis will work, we will get the so-called level 0 data. We will do the time delay interferometry to actually construct our signal, our interference signal on ground. Then we'll do the global fit on these data and get all the different parameters. So the parameters could be the directions in the sky, the angles, then the spins of the bodies, these kind of things. And then after this fit, we actually produce a catalog with directions in the sky and mapping all the different sources. And that's then basically the final product that we want to produce in LISA. That's it for LISA. And I haven't mentioned that LISA will be launched in 2035, so there's still some time to go. But already we're thinking about what's coming after LISA. And there's an active activity going on to think about what will be potential successors. And one idea is this, which is called LISA Max. What you see here is the solar system. Here you have the sun, the Earth, and the idea is to place 3 satellites close to the 3 Sun-Earth Lagrange points. So basically you create a triangle which is 100 times larger than LISA, and you will be sensitive to even lower frequencies and new sources. And there are 2 other concepts that are currently being studied. This is for the 2040s, 2050s, roughly. But these are the timescales that we are thinking in, because these projects need a lot of preparation and a lot of ideas being thought about. And that's basically it from my side. Thank you very much for your attention.
Yes. Thank you for this very interesting talk. There are a lot of questions.
Yes, thanks from me too for this interesting talk. The question is how the connection between the frequency you're measuring and the arm length is. So we thought it might be something like the one wavelength or a half ideally should fit into the arm length, but this does not match the last slide you showed and the non-linear connection between frequency and arm length there.
I didn't get everything that you said. So you're asking what is the connection between the arm length and the frequencies that you're sensitive to, and it's basically a linear relationship. So you don't think so?
Dieser Max, factor of 10, factor of 100.
Yeah. Okay, we have a factor of 10 here.
No,
Okay.
no.
Sorry, a factor of 100 here. Yeah. Sorry, and then we have, okay, it's not, it does, okay, indeed, yeah. Why does it? Yeah, I would have to think about whether this is a typo or it's true. But it's normally a linear relationship. The larger the arms, the lower you get with the frequency. Indeed, yeah, you need to fit in the wavelength of the gravitational wave into the arm. Otherwise, if the wavelength is too small, you don't see it in the detector. If it's too large, the disturbance of the two-test mass is too small. Yeah.
Hi, thank you very much for this talk. I've been excited about LISA for a very long time, and well, I guess I'll have to be excited for a while longer. I was wondering, so like what kind of data quantities is it that actually will be recorded there, like per second or whatever? And is it feasible to transfer the whole raw data back to Earth, or like how much pre-processing, pruning is going to happen like on craft?
On the spacecraft, it's not so much data that's being recorded actually. So what is recorded is the phase of not of the laser. It's a detail that I omitted. It's called heterodyne interferometry. So it's recording the phase of the beat node actually. But you can basically imagine it's recording the phase of the signal that you want to interfere. And you have the full digital signal sampled in 4 hertz. Yes, in 4 hertz. And then basically what you get, the downlink rate that you need to get down all the data is around 250 kilobits per second on an 8-hour pass. So basically you have an 8-hour ground station pass and 250 kilobits per second. It's not so much. It's the amount of data is generated on ground once you do all this processing.
Okay.
I have a question for these earthbound gravitational wave detectors. You need pretty high-powered lasers to get a signal-to-noise ratio low. Is this similar on LISA as well? And if yes, how do you cool them?
They're not that, okay, on ground-based detectors, I don't actually know what lasers they use, but on LISA, it's a 2-watt laser. Yeah. I think, I don't exactly know what the reason is. I assume that if you have a more powerful laser, it would be, you wouldn't be able to comply with the noise requirements, etc. Of course, the more powerful the laser, the less, the better. But I think there's another reason for this low power.
Okay, where was the next?
Hi. What is the angular resolution of LISA? Because if you then need to follow up with optics, so telescopes, you want to know more or less where are your sources.
Yeah, so the angular resolution of the sky localization, that's what you're asking, yeah. I don't know exactly, but it's in the order of a few degrees, like 2, 3, 4 degrees, something like that. It's not super precise, but it's getting you the general direction of where the source is.
A question from remote. From Benjamin Barr. When I left the field some years ago, my latest info was that the LISA mission was scaled down to ELISA due to budget constraints, so US leaving. And there was a discussion, the notable discussion about that the triangle configuration was replaced by an L formation. Now what you showed or informed us is that it seems like we are still on the old plan before the budget cuts. Has the situation changed?
It's right, yeah. So, as I said, and I showed earlier, there's a long history of LISA, and originally LISA was here. In the 2010th, LISA was a joint ESA-NASA mission, but NASA left the project because of budget constraints, because James Webb became so expensive, basically. And then, indeed, this downscoping was done to, people thought about, okay, how can we make this thing cheaper? And they thought, okay, well, instead of 3 arms, make 2 arms, but you don't gain much. You still have to do 3 spacecraft, and you lose a lot of science, because with 2 arms, you can do a lot less than with 3 arms. So in the end, we are now back to the original LISA mission concept, and it's expensive. It is, I think in total, it's like more than 2 billion. But it's classified as an ESA L mission. So we have the 3 categories, L, M, and S. L missions are launched only kind of twice per decade. So one L mission is JUICE, then there is Athena and LISA. So these are things you cannot do that often. But LISA is one of them.
One more here in the back.
One of the quite interesting things you're talking about is detecting primordial gravitational waves. With LISA, what categories of theories would we be able to basically exclude by measuring or looking for primordial gravitational waves?
Okay, I'm not an expert in this. I mean, I've only listened to this when other people talk about. So what people look at is like the phase transition, the electromagnetic phase transition that we know probably happened in the early universe. Then, of course, we have inflation, then cosmic strings, and probably other theories which I forgot. Yeah, each theory has their own model, and they're able to produce their spectra. It will also be difficult if you measure something. First of all, it will be low above the noise, and then how do you disentangle between the different theories? I think it will be difficult. But yeah, I'm not an expert in this.
Would it help to understand, to distinguish the different sources and to improve the angular resolution of the sources, to have a second copy of the constellation far away on the Earth orbit?
It will be, yes. And indeed, there is a second copy. The Chinese built a mission that is essentially a copy of LISA. It's called Taiji, and it has it's maybe a 3 million kilometer arms, and it's going ahead of the Earth, not behind. And indeed, if we manage to share the data, I think it will be a huge benefit for exactly for this kind of thing.
You mentioned laser noise as one of the main difficulties that you'll need to face when the spacecraft are up there. What other sources of noise are there? Is it mostly internal from the spacecraft, or do you also have to deal with like solar flares or something coming, like a cloud of gas coming between the lasers or something?
I think most of the sources are internal. Like everything that we had on LISA Pathfinder, I think I didn't mention it. So like the electromagnetic residual interference, then the gas particles, so the Brownian noise on the test masses. Then there are also external disturbances, but I think they will happen less often. Like for instance, you could have a micrometeorite hitting the spacecraft, and then at that point you have to you cannot use this batch of data essentially. Yeah. Solar flares, I don't know. I mean, they disturb all spacecraft, so potentially they could also disturb LISA. Yeah. But it's mostly internal sources, so the sources that were also investigated LISA Pathfinder.
Okay, one last question.
So with these large distances, I assume the mirrors have to be very precisely aligned, but you said they always have to be in free fall. How does this work? Because I assume there is some drift. Is there like a short window where you can record something, then everything has to be aligned again, and then free fall again, or how does this happen?
Okay, maybe I was not clear. So in LISA, the mirrors are not free falling. In LISA, the mirrors have to be still precise, the telescopes, but the only thing that's free falling is the test masses. So again, we have two test masses, and the spacecraft hovers around the test masses, essentially. And then there's actually 3 measurements per test mass. So it's not that you measure directly test mass to distant test mass. There is a bit more complicated system to make sure to have all the different contributions measured well. The test mass has to be really perfectly free-falling, but the telescopes, no.
Just swap the function of the test mass at the mirror in my head.
No, I mentioned it like that when I initially explained it, but yeah.
Okay, we're at the end of our time. Thank you, Waldemar, for being here. And this is a little thank you.
Oh, thank you.